Okay, this is an explanation of the motor coil circuit, and I'm also collecting the flyback into a capacitor, which is right here. It has an N-channel MOSFET, gate, drain, source. The power comes in, I say 4 volts to 18 volts because the power input of DC is the same, is sharing the, it's powering the Hall effect, and it's also powering the driver chip, and they can't go over 20 volts. So I'm saying 18 volts. So you can follow the red, the positive here, see it powers this, and then there's a common ground through everything. The ground is supplied for the Hall effect. Ground is here for the little gate driver chip 4421. And here's the source of the MOSFET. It's an N channel, so it's switching on the low side of the coils. I have 2 coils on each side of a flat disc rotor with 16 rotor magnets, and they're in series. And there's the timing disc that trips the Hall effect, which trips the gate driver, which trips the MOSFET, has 16 small little magnets on it. And I put this 10K resistor as it helps the MOSFET turn off quickly, but the same function's done with the chip, but I just put that in there anyways. And I have a little 22 ohm resistor, and it kind of deadens any weird stuff going into the gate. And to fill up this flyback collector capacitor, I call it, you just come right off the drain. See, as it's heading to the drain of the MOSFET from the coils, out of the coils to the drain. You just attach a wire there, put it on a very fast diode. This is HFA25PB60. It's very fast. They even have hyper diodes now you can buy, but this one's really good. I call this the flyback spike steering diode. And you put it, you see the arrow, it goes right into the positive of this capacitor, and the ground of the capacitor is connected to the shared ground of everything. So that's how you put power into a capacitor. But now when you want to discharge it, you better have this decoupled all by itself when it decouples, because right now if you just put a load on that, it'll just ruin everything. So this is the basic motor coil circuit I have going. And what will happen is this will collect the spike, but after a while it's like filled up, so it's not collecting the spike as it should. So I talk about that over here. And also the capacitor size. You need to experiment with the capacitor size, like I'd say like 12 volt input and like 8 ohm coils. You're going to need about a 500 UF maybe. You have to see. And if you have it too big, it works like resistance, and it just doesn't work very well if the capacitor is too big. If it's too small, you're not collecting all that you can. So you want to find the perfect size capacitor for whatever you're doing. Okay, so now I'm going to show some other circuits, how to discharge this capacitor into a load without affecting the draw of anything, and in fact it should make the draw go down of your motor coil input, and as it's being discharged periodically into a load, this capacitor. Okay, so hold on and I'll show those. Okay, this one I call the bucket brigade. And here's the same motor coil circuit. Here's a steering diode filling up a flyback collector capacitor, same thing coming off the drain. Everything's the same over here is what I just showed. But now what you do is you discharge you dump this capacitor into this middle capacitor, and then you dump this capacitor into the final capacitor, and the final capacitor will have the load across it. So I call it the bucket brigade. Like in the old days, they'd put out fires with a long string of people passing a bucket of water all the way to the fire, you know. So this is what this is doing. It's passing a cap to a cap. So if this is 50 volts, this will be 25, and at the end this will be 12.5. It'll be 25 in each, and then 12.5 in each. And the way I discharge it is through these solid state relays. You could do this another way if you want, but this is how I'm doing it here. These are fairly slow. I have these at 40 amps and 480 volts. You can find them like that. They have all different types of solid state relays. These have MOSFETs inside of them. And so the green wire here goes to the Hall effect. The green wire here goes to the Hall effect. That's sort of the signal that turns it on and off when that receives a little signal to it. And notice the Hall effects share a common positive, and with everything else, common positive, and then there's a common ground too with the Hall effects, common ground with the caps too. See that? So that's the way it works. And so I have two trigger magnets at 180 degrees and two Hall effects at 90 degrees. So when this spins around, when it contacts this one fires. When it spins around another 90 degrees, this timing disc, now the magnet will be here and this one will fire. And so it's alternating, and then the next magnet comes, so it goes bang, 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 like that. So when it goes bang here, that drops this capacitor into here. When it goes here, it drops this capacitor into here. And I put an inductor in series and also a diode. And that's because if you don't have those, there's a huge amount of current that bangs in from a cap discharge into another one. This is supposed to make it a lot more efficient. It's supposed to be 95% efficient. And so that's what these are here. And what else? So this is the bucket brigade. And that's about it. So on this one, so I'll show the next circuit, which is where you actually have the cap disconnected, decoupled when it discharges. Okay, hold on a sec. Okay, here's the next circuit, and this is the same thing with a motor coil circuit over here. Same thing as the other two I just showed. Two coils, 16 rotor magnets, 16 magnets for the timing disc, and a Hall effect, and you're bringing the drain out. But now there's a change here where I have two steering diodes. One the power comes into the end of each, right here, you see that? And then the two diodes split what goes into caps. This one will go into this cap, this one will go into this cap. And it's switched into the caps. In series, there's a solid state relay that needs to be closed for this capacitor to open. So see, note that this one's closed, and so this cap B is filling as it is how I drew this diagram right now. This is filling up because this solid state relay is closed. This solid state relay is open, so it is not filling up this capacitor now, and in fact this is now discharging. See, this is closed here, so this cap A is being discharged into a load at this time, how I show it here. And And I do this through using two different types of Hall effects. If you use a Hall effect 630, 1330, ND, it creates the solid state relay to be normally closed, and it switches open. So when the magnet goes past a Hall effect, it switches open. Okay, so this is normally closed, switches open. So, and it's being switched. See, it's open. So if you follow the green, it goes to this number D Hall effect for the number D solid state relay. And it's being switched open because it has a 630, 1330, ND. But now this one over here is, see, it's closed. That's because it's going to this Hall effect over here, which is being tripped by this. See, I put a single magnet on the inside, and then these only trip the outside. This one, see that? There's 7 little magnets right here. And that's supposed to be like one big magnet that lasts a long time, switching this Hall effect, triggering the Hall effect. And then I only put one little magnet, and this is the one that discharges. And so you notice the Hall effects inside, so these do not affect this Hall effect or this Hall effect. And this magnet does not affect this magnet, this Hall effect or this Hall effect. So anyways, so right now this one is being discharged. So if you follow the green wire, there it is. And see, note it's an A1120 EUAT, so that's a normally open, switches closed, so it's being switched, so it's closing. So this is discharging to load. So what I show here is the cap A is being discharged to load while it's uncoupled. It's uncoupled. It's kind of free. It's free floating because this is open. Okay, so now when this spins around, like when it goes to here, this little magnet goes vertical and this points down. Now you have the opposite thing. This one will be discharging, and it'll be decoupled when it discharges. Well, this one will be filling. So what's good about this is you're always filling a cap. You're alternating. This one discharges in a decoupled, free-floating fashion, and then while this is discharging, this one's being filled, and then the same when this one discharges, this one is being filled. So I call this alternating cap discharge. And note that the caps all share a common ground, and the ground of the Hall effects is common, all hooked to the ground. And the ground of the whole system is also hooked to the ground of the Hall effect, the ground of this, and the ground, the source of the MOSFET. So that's why I say 4 to 18 volts, because these components, the driver chip, Hall effect, they can't handle more than 18 volts. So that's as high as it goes. I'm also supplying the power to the trigger side of the relays with the positive here, with the same positive 4 to 18 volts DC input. That's all supplied there. You could have a separate power supply for the trigger side if you want. And you could do this in other ways. These are pretty slow, these solid state relays, because they're so well isolated over on the trigger side. There's other ways you could do this, but this is basically how I'm doing it, and it's kind of shows what's going on if you want to do it in another way. And what else? That looks pretty good. So this is how having a capacitor be decoupled, floating free when it discharges. I'm not putting one cap into the other. This one, you don't lose much. You lose that voltage, like if you have 50 and the one I showed before, you have 50, then it goes 25, 12 and a half finally at the load. This one, you don't lose anything because you just disconnect the capacitor from the circuit and then unload the capacitor by itself. But the problem with this, if you can call it a problem, is it had the flyback coming in has to go through a closed switch, and this is a MOSFET. And it would probably be better to have like a bunch of parallel MOSFETs, very high voltage, instead of the single MOSFET inside the solid state relay. So you don't lose anything as the flyback has to run through this switch on its way to the capacitor. But nothing's perfect. But so this is what this one's doing. So this is a way to periodically discharge caps that collect the flyback from a MOSFET into a load. And it doesn't affect the draw of the motor coils, and in fact it should lower the draw of the motor coils when you find a good size of capacitor like I mentioned in the other video. So I think this is pretty good. There's 3 circuits I just showed in this video. Okay, thanks a lot for watching.